Go.
Okay, hello Chemers, it's Mrs. Facca, back after your Hess's Law problem. And Miss Natical pointed out that I forgot that -1 on the third step. I multiplied it by -1, I just multiplied it by 1. That was my bad, sorry about that. So if you remember, enthalpy 4 ways is like chicken 4 ways. This is the chicken parmesan. So we've done Hess's Law in the previous video. Now we're doing delta H naught F, the enthalpy of formation. And this is pronounced, it's a degree sign. It's not a 0, it's a degree sign. It refers to naught, meaning standard. And that little F stands for formation. So this is a second way of calculating enthalpy. Hess's Law was one way, this is now the second way. So the formula that you should know for delta H naught F is that how we're going to calculate this is that we're going to take the enthalpy of formation for all of our products in a chemical equation, and from that subtract the enthalpy of formation for all of our reactants. So let's look at a question. So here it's going to ask, what is the delta H naught F in kilojoules for the combustion of 1 mole of ethanol? Right, so if you recall, any combustion reaction, we're going to assume complete combustion unless we state otherwise. For any combustion reaction, the only term that changes in the balanced chemical equation is whatever fuel we're using, whatever is getting burned. So in this case, it's ethanol, C2H5OH, don't worry. You'll know how to do that in Unit 4 Organic Chemistry. So we've got ethanol, which we know is really flammable. It's the alcohol we use in cooking, and it's really can be lit on fire very easily. So plus oxygen gas yields carbon dioxide and water, right? So that are going to be our products for any combustion reaction. So always make sure you balance the chemical equation before you proceed. So we're going to have a 3 coefficient in front of our oxygen, a 2 in front of our carbon dioxide, and a 3 in front of our water. So now, in order to calculate the enthalpy of formation, we have to determine what the enthalpy of formation is for carbon dioxide and for water. Whatever that term is, for carbon dioxide, we'll multiply it by 2, and for water, we'd multiply it by 3. So these aren't values you yourself can just calculate. You have to obtain these values from a table. And there's a table in the textbook. I believe there's a table in your D2L reference area. So you would have to look up the values for carbon dioxide and water, and then from those subtract the enthalpy of formation for ethanol and for oxygen gas. Okay, so we'll move to the other board to do that. So the enthalpy of the reaction, because we're actually determining it for the reaction, not one specific substance. So we've got the enthalpy of formation for carbon dioxide, if you look up on the table, is -393.5 kilojoules per mole. So big square bracket, we have a 2 coefficient because our stoichiometric coefficient in front of CO2 is 2. And the table told us that that value is -393.5 kilojoules per mole. And to that, we want to add the enthalpy of formation for water. One thing you need to be aware of, there's different enthalpies of formation for gaseous or liquid water. So in this case, we're using gaseous water. That's our default. Plus 3 times the enthalpy, which is -241.8 kilojoules per mole. The math's not hard, it's just big. Okay, and then from that, right, we're gonna take, this part of the formula, the enthalpy of the products. From that, we're gonna subtract the sum of the enthalpy of our reactants multiplied by the stoichiometric coefficient from the balanced chemical equation, right? As I always say, it's easier to show chemistry than talk chemistry. So now we're going to subtract the 1 mole of ethanol which works out, well, it doesn't work out to, it's on the table as negative 235.2 kilojoules per mole. And then our coefficient for oxygen is 3, but the enthalpy for any molecule that is made up of only one type of atom is 0, and when it's in the elemental form, it's 0, so that's 3 times 0 kilojoules per mole. So now we punch in the math, and this is where, believe it or not, is where the most mistakes get made, because this will work out to be a negative value. When you're subtracting a negative, of course, you're going to be adding the positive. So let me show you what you should get. Negative 1512.4 kilojoules minus a negative 235.2 kilojoules, right? So then that works out to be our delta H for this reaction is equal to negative 1277.2 kilojoules. So just watch for that 0 term. If a molecule is made up of only one atom or it's an element in its free state, it's always going to be 0. Watch the minusing or subtracting a negative, that's going to be a positive. And just remember, the other mistake students often make is that they forget to multiply by the stoichiometric coefficients, the n in this equation, in the balanced chemical equation. Chicken Parmesan is done. Have a good day, guys.